Hey guys, Mr. Davis here. Today we're going to be talking about the composition of the atmosphere. So we're literally going to be talking about what the Earth's atmosphere is made of, and then we're also going to look at how the atmosphere kind of sorts itself out and how it's layered. So if you recall from our previous lecture, we had a breakdown of the geosphere, how the Earth is physically structured. Well, now we're going to look at the atmosphere, so the air around our planet. So we need to first look at what is our atmosphere made of. So if we look over here, let's go ahead and see what the most common gases in the atmosphere are. So the first one, and this is also its largest reservoir, is going to be nitrogen. Yep, nitrogen makes up about 78% of our atmosphere. Now, we cannot breathe nitrogen. No living organism can really breathe nitrogen, but nitrogen is important for all living organisms because it's necessary for DNA. It's also necessary in the construction of cell membranes and proteins, amino acids, all kinds of stuff like that. So most of our atmosphere is nitrogen, but only a few organisms can actually make that usable, and you should know that from your biogeochemical cycles. All right. The second most common element of our atmosphere is oxygen, and oxygen comes in at about 21% of our atmosphere right now. And I said right now intentionally because in Earth's history, that oxygen level has gotten as high as 30%. All right? It does change, and it has changed throughout the history of life on Earth, and there's been a number of things that have affected it. Since humans have been around, it's pretty much hovered right about 21% oxygen. All right, so those add up to about 99%, you should notice. So what's the remaining 1%? Well, we've got a host of other gases from there. All right, we've got argon, which is a noble gas. It's very dense, very heavy. It makes up about 93% of our atmosphere, but it's also non-reactive, so it doesn't really react with anything. It doesn't bond and go away and become other stuff. Carbon dioxide is only about 0.063% of our atmosphere, but that small amount is actually making a big difference. All right? It doesn't take a lot of carbon dioxide in an atmosphere to fundamentally change how that atmosphere will hold heat and will hold temperature and pressure and reflect radiation back into space. And then you've got traces of a number of other gases. Neon and helium and krypton are all noble gases. They don't really react with much. Methane, or CH4, is another carbon gas. It's produced as a byproduct of decomposition and breakdown. And then you've got a trace amount of hydrogen, but most of the hydrogen that you're going to find on Earth, even though hydrogen is the most abundant element in the universe, most of it's going to be very rapidly taken up and combusted in oxygen and converted to water. But there are traces of hydrogen that can be found free in our atmosphere, free before combustion. All right, so that's a quick overview of the general gases in our atmosphere. The big ones that you need to know is nitrogen at 78%, oxygen at 21%, and then argon and carbon dioxide make up the big bulk of most of the rest of the gases. Those are the key ones that you want to know. Really know oxygen, really know nitrogen, and then know that 1% is made up of mostly argon, carbon dioxide, and a couple other things. All right? You don't need to know the detailed breakdown of these. And keep in mind, these numbers change and fluctuate throughout time, and also depending even on the seasons. Because, yeah, at different times of the year, you might have a rise or a fall in atmospheric carbon dioxide levels based on the amount of photosynthesis occurring. All right, so enough about that. Let's dive into the actual structure of the atmosphere. What does this thing look like? Okay, so our atmosphere can actually be sorted into different layers. So let's take a look at those. So I've got them arranged over there as layers, all right? And I've labeled the layers. Now, at the bottom, that's Earth. That's, bottom layer of the atmosphere. And generally speaking, when I ask you to list the layers or put them in order, things like that, I'll say going from space to the ground or going from Earth up, put the layers of the atmosphere in order. I will tell you which direction I want you to go, all right? So starting at the bottom, you have the troposphere, And that is where you live and where you will spend the majority of your life. You will rarely, if ever, escape the troposphere. Even if you climb to the top of Mount Everest and somehow manage to live there for your whole life, you would still be in the troposphere. Every mountain on Earth is still inside the troposphere. The only times that the average person is going to get out of the troposphere might be traveling on a high-altitude aircraft, and that's really only for the very long flights, and we'll talk about that in a second. Above the troposphere, you have the stratosphere, then the mesosphere on top of that, and then lastly, at the very, very top, you have the thermosphere. And the thermosphere is the topmost layer, and it actually gets divided into two layers. Now, I want you guys to take a look at that graph that I have there. You may notice that I've got a weird yellow squiggly line that goes back and forth. Well, that's measuring temperature. And the farther that that graph goes to the right, the higher the temperature is. So the farther to the right, the higher that temperature is. Okay? So look at that carefully, read it carefully. You'll notice that to the left it's negatives and the right it's positives. All right? And this is measuring the average temperature of the thermosphere across all different latitudes, so same distance, so all the distances from the North to South Pole at those altitudes. All right? So I want you guys to take a look at that and notice that that trend on how it zigzags back and forth, you're going to want to know that general trend. All right? You're going to want to know the general trend of where that temperature is going to go up, where it's going to go down, what layers it does what, general stuff like that. All right. So let's start off by talking about the troposphere. Remember how I said this is where you live? Well, yep, this is where all living things live. It's the layer closest to the Earth. It's where all the water is, all right? It is the most important layer for living things, and it contains 80% of all of the air in the atmosphere. It is the thickest layer. It is the layer at the bottom, so it's got the most pressure pushing down on it, so it is the densest layer, all right? It goes up to about 10 kilometers above the surface of the Earth in most places, although that can vary depending on latitude or topography. So it goes up to about 10 kilometers or 6.2 miles or 33,000 feet, however you want to say that. And so generally speaking, that's about as far up as it goes where you're going to get out of there and go into the next layer above it. General trend here is as the altitude increases, so the farther up you go in the troposphere, generally the temperature decreases. And you can observe this yourself. So if you want to get out of the heat in the valley, a lot of people will travel up to Flagstaff, Pine Top, Show Low, those kind of places, get up to a slightly higher elevation, and you'll notice that it gets cooler. At the same time in the winter months, if you want to see snow, that's where you have to head to, all right? It's not just because they're north of us, it is because they're at a higher altitude. Because if you go west and go up over the Rockies and Sierra Nevadas, you'll notice that it also will drop in temperature relative to us down here in the valley. All right, so that's the troposphere, all right? It's the bottom layer. General trend is the higher you go in the troposphere, the lower the temperature is going to be. Also, it's where you're going to find all the moisture, most of the air, and all of the weather. So where you have rain and storms and hurricanes, that's all still in the troposphere. All right? All right. So the next layer above that is going to be the stratosphere. And in between the troposphere and the stratosphere is this thing called the tropopause. All right? So we have the troposphere, tropopause, stratosphere, and then inside the stratosphere we'll have the ozone layer, which we'll talk about in just a moment. All right, let's take a look at the stratosphere. It's approximately going to start about 10 to 12 kilometers above sea level, again, depending on topography, so that's the shape of the land, and latitude, how far north or south of the equator you are. All right? Starts out at about 10 to 12 kilometers above sea level, and as you go up, the air does get thinner still, but the temperature is also going to increase as you go up. It's located just above the troposphere. And here's the thing about it, though. Large planes will actually travel through this layer. Why? Why would big planes want to travel through there? Why would the long-distance flights want to make sure that their flight plan takes them through the stratosphere as opposed to just the troposphere? Any ideas? Well, Because at this altitude, the air is so much thinner. This is actually above an altitude where you can survive for a long period of time without a pressurized atmosphere being put around you. So in an airplane, they pressurize the cabin so you're not going too far up in elevation. In high altitude fighter jets and things like that, they actually have oxygen masks that deliver air to them. But the reason why they're up there is because the air is so thin, so there's less friction on the plane, less wind resistance, so they can fly faster and use less fuel. So for a very long flight, so that they have enough fuel to make it, they want to climb up to the highest level that they can and then cruise at that very high altitude. It's also why some of the biggest planes that go the farthest distance have really, really long wingspans, is because they need that extra lift where the air is thinner. All right. Now, inside the stratosphere, there's a very important layer, and we want to talk about that, and that's the ozone layer. You might have heard of the ozone layer before. The ozone layer is a layer of air found in the stratosphere. Ozone is a kind of bluish color. So if you look right up above my picture there, you can see I have two containers. One has regular air, oxygen in it. The other has ozone in it, and that's the color that it makes. If you want to know what ozone is like if you encounter it in person, it actually has a smell. It has an acrid, burny kind of smell. So if you've ever accidentally shorted out a circuit, that's what ozone smells like. But what does ozone do for us? How does ozone help us out? Well, it's a layer of gas that actually absorbs ultraviolet rays coming from the sun. It protects us from these rays, which can then cause skin cancer. Oh, okay. Well, that protection from the ultraviolet rays actually heat up the atmosphere, and so the higher you go in the stratosphere, the higher the temperature gets. Yeah, it absorbs that radiation, so the heat gets trapped in the ozone layer as opposed to reaching the surface level. If we didn't have the ozone layer on Earth, you literally could not live outside. All right, it would kill you. Yeah, it would. All right, it would actually sterilize all surfaces, so all bacteria and things like that would be killed. Plants could not survive. So ozone, it plays a very, very important role for the atmosphere for that purpose. All right, so then we have the next level above that. So we have the troposphere on the bottom, stratosphere, which contains the ozone layer. The ozone layer is not separate. Keep that in mind. The ozone layer is inside the stratosphere. Then above that, you have the stratopause, which is that interface between the stratosphere. And then the next layer is the mesosphere. And I've got a really easy mnemonic device to remember the mesosphere. The mesosphere is the third layer of the atmosphere. It's about 40 kilometers thick. It starts about 60 kilometers above the surface of the Earth. And once again, here's where you're going to see a temperature that goes back down. All right, so the temperature is going to descend again as you go up in the mesosphere. So troposphere, the temperature went down. Stratosphere, temperature went up. Mesosphere, oh, it's going back down again. Okay, so here there's a wide variety of temperatures. It can get really, really crazy cold, and it's largely because there's so few air molecules. There's just not a lot to absorb that energy. All right. But there is enough there still, and because it's a big enough area, it actually protects the Earth from meteoroids. So little chunks of metal that come from space. Sometimes we call them shooting stars. So meteoroids, mesosphere, hey, that's how I remember it. That's what makes it easy for me to remember the mesosphere. And so the mesosphere is where you're actually going to have these burn up. So have any of you ever seen a shooting star? You know, you can actually see them almost any time of the year. Now, there are times of the year where you'll have meteor showers that are better than others, but this is actually from the mesosphere protecting us, all right? The trail that you see behind them, that's the gases burning off, and the color that you see depends on the chemical composition. So different chemicals in those asteroids, or meteorites, I should say, can change what color you'll see. Pretty often you'll see blue ones, and that's that interaction of magnesium. Most of the meteorites that you'll see there are that color, but another common one you'll see is iron as well, and they're a bright yellow color. Now, I mentioned that you can see these throughout the year. If you go somewhere where you can see the stars, so you may have to get out of the valley, go up to Flagstaff, Show Low, Pine Top, especially on moonless nights, and just look up at the sky. Relax your eyes as best you can. Just try to just look at as big a section of the sky as you can without focusing on any individual star. Just relax your eyes and watch. After maybe 30 seconds to up to 3 to 4 minutes, you should see at least 1 or 2 meteorites. All right? Shooting stars happen all the time. But there are certain times of the year, and you can definitely check online calendars for sometimes when you can get really good showers where that frequency rate goes up to anywhere from 5 to 20 meteors per minute. And those are really cool to see. So if you ever have the chance to do it, I definitely recommend it. All right, let's get back to the atmosphere. All right, so review our layers. Troposphere, Stratosphere, Mesosphere, Mesopause, and then on top of that is going to be the next layer, the Thermosphere. All right, last layer we need to know, but I'm going to trick you here, and I'm sorry. The Thermosphere is the last layer. It is the 4th layer. It is the thickest layer. It is over 90 kilometers thick. The sun rays in this zone can create extremely high temperatures that exceed over 1,000 degrees Celsius. So you see the astronaut there working on the International Space Station. He's wearing this big bulky suit. Well, that suit isn't just to keep the atmosphere in around him. That's to protect him from all the temperature changes. Because when he's in the shadow of the space station, he's going to be experiencing temperatures that are as low as, you know, negative 270 degrees Celsius sometimes. Maybe not quite that cold, maybe 268 Celsius. Either way, still really cold, about 5 to 6 degrees Kelvin. Crazy cold. But as soon as he goes back into, you know, the sun, all of a sudden he's got no protection against just raw solar radiation. And he can go over 1,000 degrees Celsius. Now, can you imagine? He's reaching one arm out into the sunlight and the rest of him is in the shadow. His suit has to be able to accommodate that and handle that. And that's really why those spacesuits are so bulky. All right, so we got 2 layers to this, all right? The lower layer is called the Ionosphere and the upper layer is the Exosphere, but they're both part of the Thermosphere, all right? So the Thermosphere gets divided in half because it's so big. And the properties change a little bit. So let's work through that. All right, so the ionosphere is at an altitude of 90 to 300 kilometers, all right? It is part of the Earth's communication system because it contains electrically charged particles, and they bounce radio waves. So what we can actually do is using just regular radio waves is we can bounce them off of these, and at night you can actually get signals traveling a lot farther by simply bouncing them around the globe. And this is how we used to have to communicate long distances before we had satellites. We had to wait till night and transmit and retransmit at specific hops so we could send messages all the way around the planet. All right, then you have the other factor here, which is the northern lights, or the aurora borealis. Now, you do also have the northern lights in the southern hemisphere, only they're not the northern lights, they're the southern lights, or the aurora australis, all right? They're caused by charged particles in the upper atmosphere getting struck by radioactive particles. Now, I say radioactive particles, but they're actually nuclei. They're actually broken up particles of the nucleus of an atom. Sometimes they're fractions and parts of things like protons and neutrons, all right? As those particles with a lot of energy traveling at near the speed of light strike the particles of oxygen and nitrogen in the atmosphere, they cause them to glow. All right, and that's how you can get those beautiful green and gold and even red colors that you can see in the northern lights. So when it occurs, now, I have sadly never had a chance to see this myself. I've always wanted to, but I'm a wimp when it comes to the cold, and unfortunately, it's at very specific times of the year when I'm teaching. So it occurs year-round, but doesn't mean you'll be able to see it year-round, all right? Best time to see it is actually in December to March, when the nights are the longest. The colors will vary. Yellow, orange, green, and red is the rarest. You can also see purples and blues and things like that. The picture that I've got up is an actual true photo of the northern lights. That's what it can actually look like. It occurs in a ring-shaped region around the north and geomagnetic poles. And when you have a level of high solar activity, so you have solar flares and things like that, you have a better chance of seeing those northern lights because of the ejection of coronal mass, those charged particles coming off of the sun. All right. So there's another really cool thing that the atmosphere does. It's another fascinating condition that you can see here on Earth, demonstrating how the atmosphere functions for us. All right, guys, so this is the last part of the atmosphere. This is the last part of the layer that you need to know. So remember, we're in the thermosphere. We're now above the ionosphere. We're up where there's almost no particles, all right? Very, very few particles, but there are small amounts of atmospheric particles out here still. And in fact, while we will say that the Earth is largely a closed system, there are bits of our atmosphere that are actually stripped away by what's called the solar winds, by the action of just us hurtling through space, by loss and attrition from collision with space particles as well. So this is the exosphere. This is the outermost layer of the thermosphere. This is where satellites are because they have pretty much no atmospheric resistance now, so they can stay up for a longer period of time. The higher up they are, the longer they can stay in orbit. This is also where you're going to find space stations, the International Space Station, things like that. This can extend up to 10,000 kilometers from the surface of the Earth. All right, so this is very, very, very far up. This is actually above where the space station is at its farthest out point, but this exosphere is the outermost part, and here is where you're going to find those super high temperatures when you're in the sun, because there is nothing to protect you from the sun at this point. You're just getting that straight, pure solar radiation at its highest level of intensity. There's nothing to absorb it before it gets to you. So it's actually much higher radiation here, which is why solar panels are equipped on so many satellites, is because they work actually much more efficiently sometimes in space because they are able to absorb that sunlight very quickly. The problem they then have is just making sure they stay cool so they don't melt or lose conductivity from exposure to excess heat. All right, so that's our atmosphere. That's a look at everything from the surface of the Earth up to space. And you can see the haze of the atmosphere here with this picture taken from the robotic arm of the orbiter. And that's us. That's the whole planet right there. And so the question is, do we have to protect our atmosphere? Is there something that we have to save here? Can the atmosphere take care of itself? We talk about, rising carbon dioxide levels and things like that, but, it's only 0.0036%. That's not that much, right? Well, there are some things that we are doing that are having an effect on our atmosphere. So I want to touch on one last thing here, which is the environmental damage to the atmosphere. And this is an easy example to show you, all right? So let's start off talking about the ozone layer again. So the thickness of the ozone layer is shrinking because of CFCs, chlorofluorocarbons. These are hydrocarbon chains, so it's links of carbon atoms together, okay, that are then bonded with fluorine and chlorine that make them into these ring formations that are very, very stable. They were used in aerosol products, and more importantly, they were used in air conditioning, all right, because they can very rapidly expand and contract. They were really, really good at being used to heat and cool homes, all right? So what's the problem with thinning the ozone layer? Okay, we got to go back and remember what the ozone layer does for us. Hey, that's an ecosystem service. That's a term you want to know. Ecosystem services, things the ecosystem does for free. All right, so what's the problem here if we have a thinner ozone layer? Well, it protects us from ultraviolet rays. If you have a thinner ozone layer, you have an increased risk of skin cancer. And skin cancer can metastasize and become other types of cancer, and it can kill you. People die of skin cancer. The #1 most lethal cancer in Australia is actually skin cancer, all right? So if the ozone increases at low altitudes as well, which is sometimes produced as a byproduct of industrial activities, it's a byproduct of transportation, so it's produced from interaction of exhaust from cars and things like that. That can also cause health problems. Ozone, direct exposure to ozone is bad for your lungs. It can make you extremely sick, cause skin, eye, and mucous membrane irritation. So that's your inside of your nose, inside your mouth, your eyeballs. Those places can all get really irritated and burn. Can trigger asthma attacks, all sorts of stuff there. But a small bit of good news, all right? Well, the ozone layer is starting to heal itself. Ozone is produced naturally from the interaction of oxygen atoms in the upper stratosphere with ultraviolet radiation. So as it's produced, it absorbs some of that heat. That ultraviolet radiation prevents it from reaching the surface of the planet. By banning the use of CFCs about 30 years ago, we have now reduced the hole in the ozone layer to a much, much smaller level. Just this past year, the hole in the ozone layer was the smallest that it has been since 1981, pretty much since we've been tracking it, all right? So this is a really big deal. We are actually managing to affect meaningful change on our environment through good legislation and removal of harmful products. This is something that we can be proud of, but it doesn't mean we can just say, oh, we won, time to go home. It means we need to continue to work. We need to continue to try, and there is a light at the end of the tunnel if we put our effort into it. All right, guys. So for once, I actually get to end on a happy note. Don't get used to it. I have a tendency to be a bit of a downer. Sorry. But that's where I am going to end today. All right. So those are the layers of the atmosphere. Just to review, you want to make sure that you know the layers of the atmosphere: the troposphere, stratosphere, mesosphere, and exosphere, going from the bottom up. Know that the ozone layer is in the stratosphere, that meteorites burn up in the mesosphere. Troposphere has all the weather and most of the water and almost all of the atoms. And then the outermost layer, the exosphere, has the the outermost layer of the thermosphere has the exosphere and the ionosphere. All right? Okay, that's all for today. Take care. I'll see you soon. Bye, guys.